Thank you for the invitation. Today I want to talk about Feynman graph integrals on Kahler manifold. So this is joint work with Junrong Yan. So let's start with the motivation. So our motivation is from the following theorem, which is proved by Cauchy, arXiv, and Singer. So the content just is that Feynman graph integrals are convergent in certain type of topological field series on closed manifolds. For example, Chen-Simons theory. So this theorem have many applications. For example, perturbative invariants of three manifolds and links. Cauchy also use those Feynman graph integrals to prove the quantization of quantization theorem of Poisson manifolds. So from this theorem, we can see that Feynman graph integrals in topological field theory is quite useful. So so we can ask the following question: do we have similar results for holomorphic field series? So if yes, if we can we find some applications of this result? So we are expecting similar result to this tool. Yeah. So as a first step, we prove the following theorem. I will explain all the terminologies later, but now I will. Now the theorem is for holomorphic field series on real analytic Kahler manifolds. Okay. Sorry. For closed real analytic Kahler manifolds, the Feynman graph integrals are convergent in the sense of Cauchy principal value. So
the previous theorem was for Chen-Simons, was for which theory?
For example, for Chen-Simons theory or Poisson sigma model or one-dimensional topological quantum mechanics, yeah, many other examples. But
those are in low dimensions, 1, 2, and 3.
I think it's true for higher dimensional case, but they only worked out the 3-dimensional case, but apparently their technique are much more general.
Okay. And those manifolds need to be real analytic, just smooth manifolds.
In their theorem? No.
C infinity manifold.
C infinity manifold. Yes. Okay. I should mention that for any Kahler manifold, for any closed Kahler manifolds, we can always find some real analytic representative of our Kahler class, such that we can have a real analytic Kahler manifold. That's always possible. So real analyticity is not a severe requirement. And for example, all the Calabi-Yau manifolds are real analytic. So yeah, we add this assumption just for some technical issue. Okay, so let's explain the terminologies appear here. So for simplicity, we consider a special case of our theorem. So let M be a closed Calabi-Yau manifold with Calabi-Yau matrix. And so we have a holomorphic volume form, which is denoted by omega. And we use E tilde to denote the exterior power of the anti-holomorphic 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 cotangent bundle. So the sections of this E tilde is just the double double complex or double resolution of structure shapes. Okay, now the propagator is defined by these two equations. So propagator is just some differential form on M cross M, whose form factor just contains anti-holomorphic part. And the propagator can have some singularity along the diagonal. And so the propagator satisfies these two equations.
Box times. Yeah.
The box time just means the exterior tensor product of vector bundles. For example, a section of this. So if you have a section of E tilde. Oh, okay. Let me just write it down. So we can consider map M cross M to M, and the E tilde is a bundle. So this is we have two projection maps here. So one is pi1, the other is pi2. So E tilde box times E tilde equals the pullback of E tilde along pi1 tensor the pullback along pi2. Okay. Okay, so the first equation just tell us that if we apply the double differential to our propagator, we will get delta function minus the harmonic projection operator. So this two, this delta function is just the integral kernel of the identity operator, and this H is the integral kernel of harmonic projection operator. The second condition is not that important, but if we impose this condition, we can show that our propagator is unique and exists. So we have a unique propagator. That's why we impose this condition. Any questions for now?
Yeah, that's basically the gauge fixing.
Yes, yes. Okay, so let's look at the following example. Assume we have some directed graphs. For this graph, we have 3 vertices and 3 edges. For each vertex, we can assign a point on our manifold M, Calabi-Yau manifold M. So for this vertex, we assign Z1. For this, we assign Z2. For this, we assign Z3. Then for each edge, we can assign a propagator. For example, for the edge from 1 to 2, we assign this guy, PZ1, Z2. And for this edge, which is from 2 to 3, we assign PZ2, Z3. And for this, we assign this. And for each point, we assign the holomorphic volume form, omega Z1, omega Z2, and omega Z3. Finally, we multiply them together and perform do the integration over configuration space of 3 points, because we have 3 vertices, so we have 3 points. So that's the formal definition sorry, that's not a rigorous definition for now, because now we don't know whether this is convergent in the sense of the big interval, right? Yes, but formally that's the definition of a Feynman graph interval. So before we state the mathematical definition, let me introduce the general case. So in general, we should have a directed graph, and we should fix an ordering of all the vertices and edges, and we can have two natural maps from the set of edges to the set of vertices, which are the assignment of tail and head to each directed edge. So with these notations, we can formally write down the definition of Feynman graph intervals. Okay, so now I want to introduce another concept.
Oh, I'm sorry. Could you go back to the previous page?
Yeah.
Yeah.
Yes,
so I missed the first couple minutes, unfortunately. So what exactly is M pre-specified to be here?
Here M is a Calabi-Yau manifold.
Okay, but a priori your Calabi-Yau manifold has nothing to do with the Feynman graph hypersurface.
Hypersurface.
Yeah, I'm thinking of the usual way where you take a Feynman integral and you reinterpret it as integrating over a Feynman graph hypersurface.
Maybe you are talking about Feynman path integral, I guess.
Yeah.
Yeah. But that's not what I want to talk today. I want to talk about Feynman graph integral. Yeah, which just means those integrals appear in perturbative quantum field theory, not not
right. So you're going to integrate over a configuration space always of points on a Calabi-Yau manifold.
Yes. Yes.
Okay. Thanks.
Okay. Any other questions? Okay, now I also need to introduce this concept, which is called fake distance function. So fake distance function is just a non-negative function, such that its square is smooth function, and the 0 point of a fake distance function is just given by the diagonal. And moreover, we can always find some open neighborhood of our diagonal, such that the fake distance function is just equal to the distance function of a. So the purpose to introduce this concept is that the square of distance function may not be smooth function over all over M cross M, because we may have some cut points, cut locus. Okay. So with this concept, we can state our theorem. So given a directed graph, the following limit exists. So for the integrand, we have two factors. This factor is just the factor of a Feynman graph integral. And this guy is just some cutoff function, which depends on epsilon. So this function basically means if Zi and Zj are close to each other, then chi equals 0. If they are far from each other, then we can get 1. Yeah, and we use epsilon to estimate the distance between our configuration space of point and the diagonals. So finally, we can take the limit. We can let epsilon go to 0. The content of this room just this guy convergent. It's convergent. Yeah. Moreover, the limit is independent of the choice of a fixed distance function.
Sorry, so if we remove the pi epsilon, and so that you said earlier that we don't know if that integral converges, right?
Yes, because at diagonals we may have some singularities. But if we remove diagonals, we can get an integral over a compact set, right? If we remove some open neighborhood of diagonals in our configuration space,
And so that should be the configuration space of M minus the open neighborhood of the layer.
Yeah, yes, and the open neighborhood is defined by this. Defined by the.
I see. Okay. Yes. I understand.
Yeah. So you may ask whether it's possible to change the definition of this guy. I don't know. What I can say is that in general, this integral is not convergent in the sense of the big integral. But for many regularization, we can prove the convergence. Yeah, for example, heat kernel regularization. Okay, to explain why this term is might be useful, I want to recall some facts from 3-dimensional topological fields, right? So now let M be a 3-dimensional rational homology sphere with a matrix. The propagator is defined as a distribution valued differential form. So the only difference is that we replace the double differential by Durham differential. And because we are working with we are working on a rational homology sphere, so the harmonic projection operator can be written in a more simple form. So this guy is just a volume form, the volume form on M. So the harmonic projection operator is just the difference between the volume factor at omega minus the volume factor at Z. So for directed graph with some distinguished vertex 0, if we choose 2 vertices, we can define the propagator in this way. So this new propagator is the sum of these 3. Why do I need to introduce this guy? Because this new propagator is nicer because it is closed under the Durham differential. Why this is true? Because if we apply this operator to p hat, so on the right hand side we should have some delta function and some factor which looks like this, and this factor will cancel each other. So we only have the factor of delta function. But if we restrict this different form to configuration space of 3 points, we can get a closed form. So this indicated that we may define some invariants, topological invariants. So similarly, we can define the Feynman graph integral in this way. So for each edge, we associate our modified propagator here. And now we assign the distinguished vertex the volume form, but we don't need to assign volume form for each point in this case because this guy are given by differential forms. But unlike in holomorphic field theory, these are given by the anti-holomorphic part of only contains this factor only contains anti-holomorphic part in holomorphic case. Okay, so now let theta be the following graph. So it looks like this. Now, there's a theorem tell us that if our graph gamma satisfies some relations, then the Feynman graph integral plus some modification given by the Feynman graph integral with respect to theta graph, then we can get a topological invariant.
Also graph complex, it's just contracting the page.
Yes. Yes. So if we have a graph, we can define a differential acting on this graph. This is given by contracting edges. So for example, we can label this vertices, and we can contracting these two edges. This is plus. And we can also contract these two edges. So on and so forth. For this example, we can get 0. So this graph is a closed cycle. So the theorem just tells us that if gamma is a trivalent graph and gamma defines a co-cycle of the graph complex, then this guy is a topological invariant. Sorry, my graph is not a trivalent graph, but it's a co-cycle. Yeah. So we can ask in the holomorphic case whether we have similar result. First, we observe that in holomorphic case, our Feynman graph integral is an invariant of Calabi-Yau matrix and holomorphic volume form. That is because our propagator is unique. So it only depends on our matrix and holomorphic volume form. So the question is, if M is given by a 3-dimensional closed Calabi-Yau manifold, which satisfies this condition. This condition is similar to the condition of a holomorphic volume form. Rational homology sphere. The only difference is that we replace Durham cohomology by double cohomology. So the question is, can we construct the invariance of a complex structure by similar ideas? So I don't know the answer because the calculation in holomorphic field theory is much more complicated than topological case. But we can expect such result because in physics literature, So in physics literature, people conjectured that there exists some holomorphic field theory, which is called Cordella-Spencer gravity theory. And the Feynman graph integral of Cordella-Spencer gravity should give us complex structure events, which should be the mirror invariants of Gromov-Witten events. So it should be true. Yeah, but we don't know the answer for now. Okay, so now I want to explain how do we prove our main theorem? How did we prove that? So first I want to introduce some general Cauchy principal value. So let X be a complex manifold, and D is a simple normal crossing divisor. Now we can introduce the following definition. A differential form alpha on X with divisor singularity D is a differential form on X minus D, such that locally the singularity along D can be described in this way. So here, let's first look at the dominator. So this is the holomorphic function defines our divisor. So it can be written as a union of some hyperplanes. And for each coordinate here, the one, we can take their absolute value and put it into a logarithm and take some power of it. Then we can get the numerator. The power k and the k1, k2, km has no relation. So they are independent with each other. Here, B is just a smooth differential form. So that's a definition of differential forms with divisor singularities. Any questions? So our claim is that for this type of differential forms, we can define the integral over X. That's why we introduce this. Okay, let's move on. So now let's assume X is just given by Cn. Let J be a positive smooth function on Cn. Beta is a smooth differential form with compact support. Then we can consider the integral of this guy over this region. This region simply says that we want to perform the integral over a domain that removes the divisor. Yes. And then the claim is that if we let epsilon goes to 0, then this guy is convergent. And moreover, the limit is independent of G. So here we can say G will affect the shape of our domain. Yes, but our limit does not depend on G. in particular, this limit will not depend on the coordinate transformation, because once we perform some coordinate transformation, our divisor will differ from a factor G. So we can we denote this guy by using this symbol. Any questions?
For n equals 1, is that a familiar kind of principal value?
Yes, yes. For n equals 1, that's familiar. And I think this proposition is not new. But our proposition might be a little bit different from what you can see in literature for our purpose. But the proof is quite similar. So in general, if we have a complex manifold with a simple normal crossing divisor and some compactly supported differential form with divisor singularity, we can use partition of unity to define Cauchy principal value. Of course, you can prove this definition does not depend on the partition of unity. Okay.
If we just have C, line C,
Yeah.
and the divisor is just 0,
Yeah.
point, what's the simplest integral that illustrates this principle?
Okay, so the idea is the following. For example, we can consider this guy. We want to perform the integration over this domain. And oh, sorry. This function should depend on two parameters, z and z bar. So the basic idea is that although this guy is divergent in the sense of the big interval, we can always combine these two. We can always combine these two and rewrite it as 1 over z to the power n minus 1. And I should have some factor here. 1 plus. Okay. So if we combine these two factors, we can always rewrite them in this form. And then we can use integration by part. Okay, I think it's quite obvious we can get something looks like this. And we can notice that the order here decrease. And the wonderful thing, the most important thing is that if we let epsilon goes to 0, then this guy vanishes. The residue part just vanishes. You can prove it by perform the Taylor expansion and rewrite your integral in terms of polar coordinates, and you will find you will get some factor which looks like exponential of theta times some integer, and though this integer you can prove that must be greater than 0. So after you perform the integration, this guy vanished. So that's a basic idea. So you can apply this procedure several times, then you will get the bigger integral. Yes.
Converse and this parameter has this technique of rewriting tool. Is this just the same?
The same thing, yeah. Okay. Now let's go back our setting. So M is just a closed Calabi-Yau manifold. And we use this notation to denote the blow up of M cross M along the divisor, along the diagonal delta. Because we want to use what we have introduced, but diagonal is not a divisor, so a natural idea is to blow it up, right? So our main theorem is given by this. The propagator P is a differential form on this blow up space with divisor singularity along the exceptional divisor. So unfortunately, the proof of this theorem is quite technical. It uses heat kernel expansion technique, which is very similar to the proof of Atiyah-Singer index theorem. Yeah, because we introduced some scaling technique and reduce the problem to flat space case. Yeah. Okay. So with this theorem, it's quite easy to generalize this theorem to configuration space. Now let's introduce a compactification of a configuration space of an endpoint. So the basic idea is we want to find out some compactification of configuration space of endpoint such that if we remove this open part, then what left is just some simple normal crossing divider. So this is a famous construction given by Fulton and McPherson. So we can consider all the blow up along some diagonals, and we consider the embedding from configuration space to this blow up space, and finally we take the closure. We take the closure of this map I. Then we will get Fulton-McPherson compactification. Okay. So Fulton and McPherson proved that this compactified space minus uncompactified configuration space is just a simple normal crossing divider. So from our theorem, it's quite natural to give this corollary. The integrand of our Feynman graph integral is a differential form with divisor singularities. So in particular, the Cauchy principal value is well defined. And moreover, we can prove that on the blowups of M cross M along the diagonal, a fake distance function is locally given by this form. So therefore, we can say that the Cauchy principal value is equal to the limit we have introduced before. So that's the proof of our main theorem. Any questions on that? Okay, so here's the remark. All the results can be generalized to close the real analytic Kahler manifolds with holomorphic Hermitian and vector bundles. This is because this theorem has nothing to do with Calabi-Yau structure and holomorphic volume form. It's just some description of singularities. So now I want to introduce another approach. This approach is actually what we really want. Now let me introduce the heat kernel. The heat kernel is defined by these two equations. This should be quite familiar. And we have the following lemma. First, we can construct the propagator from the heat kernel. So our propagator can be given by this formula. HT is just the heat kernel, and we apply some differential operator to H and perform the integration over T. Then we can get the propagator. And the second statement just says that if we add some extra factor, actual term, such that this term is a zero form with respect to T, then our integral is unchanged. That's almost a trivial fact, but it turns out that this guy is quite important in our formulation. Okay, so so we can introduce a definition for this integrand. So this PT is given by this, and we call T the Schwinger parameter, and we have this guy. Then the Feynman graph integral is formally given by this. So here we replace all the propagators by TT. But for the integration domain, we integrate it over configuration space and the space of Schwinger parameters. Now we want to just consider this guy, this integrand. That means we want to integrate over the configuration space, but not the Schwinger parameters. So we should get some differential form over the parameter space of the space of Schwinger parameters. So we define Feynman graph integral is given by this guy. And we can make the following claim. For any L, there exists a natural compactification of the space of Schwinger parameters, which is denoted by this, such that our Feynman graph integrand can be extended to a smooth differential form on this space. Moreover, the Feynman graph integrand is integrable over this guy. So we just let L equals infinity. So this guy is well defined. And this natural compactification is called compactified Schrödinger space. Actually, we have already constructed this space, and we proved the following theorem. When M is just given by a flat space, although this space is not compact, but somehow we can still define Feynman graph integrals and prove similar theorems. So the consequence of this theorem is that when M is just given by a affine space, then this claim is true. Yeah. And recently, I think we already have enough idea to prove our claim, but yeah. We can prove that if this claim is true, then the Feynman graph integral defined in this way coincides with the Cauchy principal value we defined earlier. So let me describe the construction of a. Sorry, I have. Okay. So let me describe the construction of the compactification space. So let's look at this case. So our graph has exactly 3 edges. In this case, the space of the space of Schrödinger parameters is just given by this. So we have 3 different axes. This is T1, this is T2, this is T3. This is the origin. First, we can perform the real blow up along this point, along the origin. Then we can apply the blow up along all the axes. This is what we get. That's a compactification. Now, we denote this boundary. We call this boundary component minimal boundary component, because this guy is more interesting for physicists and mathematicians, I believe. Okay, so let S be the minimal boundary component. Then we can consider the integral of our Feynman graph integrand over S, over the minimal boundary component. This is well defined because this guy is a smooth different form. So this quantity in the physical set are the anomalies of holomorphic quantum field theory. Yes, more precisely, this is the failure of quantum matter equation in Batalin-Vyakovsky quantization. In the mathematical side, hierarchical operations. This defines the hierarchical operations in Kyle algebras. Of course, these are also in higher dimensional case. Yeah. So maybe we can look at the simplest case. Let's assume. So let's assume our graph is given by. So this graph. So this graph have 2 vertices and 1 edge. So we assign it some propagator. And this convolutor can be rewritten in this way. Kernel plus some kernel here. So this guy is PT. We can consider the integration of PT over M cross M, of course, yeah, and from the integral at t equals 0. This is just the index. The index of the of this operator, of this differential operator. Yeah, this is just the RTR index. So by this observation, we can expect some interesting stuff with this general setting. So
Like this.
that's all.
Any questions? I have a question. So I suppose your like finite integral also can also like include case where you have different
Topological.
no, in the homomorphic case you have like differential acting on the parameter.
Yes, of course. Similar thing. It's true. Yeah. The reason I didn't consider higher differentials is that in curve space, I cannot find some natural operator that is coordinate independent. That's why I didn't introduce that. But it's still true. Yeah.
And prove that the Cauchy principal value is coincide with this trigger primary definition in the flat case.
We proved that by proved the convergence of a Feynman graph integral in zeta function regularization. So which is basically says that if you still remember this formula, then I want to add some extra factor here. This is t to the power s, maybe -1. I don't remember that. Then we can still consider the integration over this. So by introducing this, we can observe that when s is it's much greater than 0, then this guy has no singularities. So all the this is because all the negative powers of the heat kernel expansion just vanishes. So we only have positive powers. So we can use this guy. We can use this guy to construct the Feynman graph integrals and prove that our Feynman graph integral is meromorphic with respect to this parameter s. Then we can evaluate our Feynman graph integral by let s equals 1, and you can prove there's no singularities. So s equals 1 is a well-defined operation. But by using this formulation, you can easily prove that zeta function regularization coincides with Cauchy principal value, because if s is very large, then our integrand is integrable in the Lebesgue sense. So we can use Fubini theorem to prove Cauchy principal value coincides with this guy. And on the other hand, we can prove zeta function coincides with hidden kernel approach. Because if we integrate over all the configuration space, we know that what left is just some smooth different form. If we multiply this factor, we still have a smooth different form. So yeah, it's still integrable, and we can again use Fubini theorem. Yeah, that's the basic idea. Do we have question from Zoom?
Yeah, I do have another one. So I remember this old work of C. Lee where he was doing something similar in the elliptic curve case.
Yes.
And was able to show that quasi-modular forms resulted.
Yes.
Yeah. So what do you expect for compact Calabi-Yaus, a K3 surface or Calabi-Yau threefold? What sort of recognizable invariants, let's say in B model or period terms, are you expecting to see computed by these invariants?
Of course. Our result is supposed to be used for all holomorphic field theory, and the BCOV theory is just an example of a holomorphic field theory. So if one can show BCOV is a well-defined quantized holomorphic field theory, then our approach applies. So anything computed from BCOV theory should be Feynman graph integrals we considered here.
Right. Okay. So, but in particular, you mentioned the possible application to mirror symmetry, where you expect that what you're doing is computing, in some sense, by hand or by direct analogy, the Gromov-Witten invariants, but purely on the B model side.
Yes.
Right.
But
but does that mean that one could set up a calculation where, in effect, you take the quintic mirror Calabi-Yau threefold as your M, and you literally run your calculations for various graphs and relate them directly to the periods of the Calabi-Yau, which we know express the Gromov-Witten invariants under mirror symmetry?
I think if you compute these integrals by hand, that will be very difficult. So people often prove some recursive formula for this Feynman graph integrals, and the hope is by solve those recursive equations, we can get many invariants. That's the hope. And for elliptic for the case of elliptic curve, I think Pen Yang has showed that the Feynman graph integral has a recursive algorithm, but in general we don't know.
Okay, thank you.
Yeah, but from physics literature, we know there's an equation called holomorphic anomaly equation. By using that equation, we can at least partially compute Feynman graph integral.
Great, thank you.
So no question, let's thank the speaker, please. Thank you. Thank you.